Hi, everyone. Thank you for joining us today. We'll get started in just a minute. We're going to give it a sec so other folks can join us, but thank you for waiting. Okay, it looks like we have some people rolling in, so we can go ahead and get started. So on behalf of the Environmental Finance Center Network, welcome to the 5th session in our 2022 Water Loss webinar series, Taking Action to Address Real Losses. My name is Avery Davis from the Syracuse University Environmental Finance Center, and I'm going to cover a few housekeeping items, and then we will begin. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording, our evaluation, and other information you may need. You can also download the slides from today as well as an applied activity in the Handouts tab in your GoToWebinar control panel. This session has been pre-approved for continuing education credit in the states of Tennessee, Indiana, and California. Attendees from other states can self-submit this training for credit, but we cannot guarantee it will meet your PDH or CEU requirements. It is your responsibility to check with your licensing agency to see what you need to do to receive credit for your attendance. To receive a certificate for this session, you must attend for the entire session, participate in all polls, and register and attend using your real name and unique email address. Group viewing credit will not be acceptable. Certificates will be sent via email within 30 days of the webinar date, and you can use this document to self-submit for credit. If you have questions or need assistance, please contact us at smallsystems@syr.edu. Now for a little bit about the Environmental Finance Center Network. We provide training and technical assistance to small public water systems in all U.S. states and territories to help local water systems achieve their goals and stay in compliance with the Safe Drinking Water Act. If your community or utility needs assistance with drinking water system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, we can get started. So I would like to introduce Don Nall and James Markham, both research engineers from the Southwest Environmental Finance Center at the University of New Mexico. So Don, I'm gonna make you a presenter and we can begin.
Great, thank you. All right, everything should be showing now, so off we go. So we just want to take a second and tell you thank you so much for your continued attendance in this water loss control webinar session and series. As was mentioned, this is the 5th part of this series, so if you've missed any of the series, you can catch up on the recorded versions of the webinars, and we'd be happy to point you in that direction if you have a question about where you can find those. I'm Don Nall, and with me again today is James Markham. We're both research engineers at the Southwest EFC, and our mission statement is promoting self-reliance through innovative training and assistance focused on actionable results. We do spend a lot of time working on water loss control issues, and we're really happy that you could join us again today. So maybe I jumped the gun earlier. This is the 5th session, and today we will be talking about using the audit and other tools to quantify real loss, and then talk about taking actions to actually address real loss. So we talked about apparent loss in the previous session. We've talked about the audit and how to complete the audit. Now we're going to focus on real loss issues. And just a reminder that if you want to get your CEUs, you need to participate in our poll questions today. It's how we measure engagement. So if you're from one of the states that has the pre-approved CEUs, or you're planning on self-submitting, we need to make sure that you participate in the poll questions. So we'll try to make sure that you're aware they're happening and ask you to participate. We're going to spend the next few minutes reviewing real loss, what it is, where it comes from, and how the audit addresses it. So real losses are also called leaks, right? So they can occur as leaks on the mains, the service lines, or at the tanks. Real losses are calculated when using the audit based on all the other volumes that you enter. Since the real losses are calculated, they can't be broken down based on the water balance or the water audit. This is important for you to understand. The real loss value is calculated based on your inputs. There's no way for the audit software to give you any additional information about that value. When you're in the audit software itself, the real losses are calculated at the bottom of the reporting worksheet. So let's take a look at what the water audit does tell you about real loss. So if we go back and we look at that water balance again, the real loss is the outcome of that whole balance. It's that calculation based on your inputs for all of those other boxes. Since that value is calculated, you don't enter a validity score for real loss, but every other input does affect the validity of this number. So how does that actually affect it? Well, let's take a look. If any of your inputs isn't perfectly accurate, the errors are going to show up in the real loss numbers. So for example, if you undercounted your inputs, your volume from owned sources or water imported, then your real losses will be undercounted. On the other hand, if you overcounted your inputs, your real losses will also be overcounted. Then if your outputs, like authorized consumption and apparent losses, are undercounted, your real losses will be overcounted. Or if those inputs are overcounted, your real losses will be undercounted. If you have errors in your inputs and your outputs, your real loss is going to reflect those errors, and it could be going up with one error and down with another error. So the number reported in the audit is only as valid as the data that you enter. This is why you should look at your data and assess its validity so you understand what next steps are the right next steps for your system. And the Southwest EFC is also happy to help assess your data validity and make recommendations on how you can improve it over time. When you complete your audit, you can take a look at your water balance within the software, and you'll note that the water balance states that the real losses are not broken down beyond the real loss volume. So you have to decide what you're going to do with that number. If you're using default values and apparent losses, that means your real losses are based on some assumptions for apparent loss. And this free audit software wasn't meant to give you extremely specific numbers. It is one tool that you can use in the toolbox, but you have other tools in the toolbox that you can also use. And we're going to look at the breakdown of real losses and what those other tools are as we go on today. We also wanted to point out, as you might recall from the last webinar when we discussed apparent losses, that real losses are valued at the variable production cost, while apparent losses are valued at the customer retail cost, unless you choose to select to value your real losses at the customer retail cost. So when the two are valued differently, there can be real differences between the volumes of losses and their corresponding values. And of course, in version 6, they put the comparison side by side. So you can see here in version 6, the real loss is on the left, the real loss volume is on the left, and the corresponding real loss value is on the right. And you can see that the difference in the valuations can be significant. So for example, in this particular example here, the theft volume on the left is part of your apparent loss component, and it's almost insignificant here when compared to the volume of real loss. But because it's valued differently, it's valued at the retail cost. It has a relatively, it's a relatively small volume, but the value is almost equal to the real losses in this system. So we really want you to think about not just the volumes, but the values, the dollar amounts kind of associated with them. And how are you valuing those? Are you selecting to value real loss at customer retail prices? Or are you selecting to keep them at the variable production costs? There are reasons for both, and we would like to have a conversation with you if you're not sure how you should value them, and maybe talk about which audience you're presenting them to. So there are different times when it might be appropriate to use the different values. And if you've got questions about that and would like to talk to us about it, we'd love to talk to you about it. It's a good question, and it's a good thing to ponder and to think about who you're sharing the information with and how you should be using it. So we've mentioned that real losses are those leaks in your system. So let's talk about those a bit more in depth now. So the first category of real loss is breaks on your mains and your transmission lines. So some number of main breaks are basically unavoidable. The catastrophic main breaks are often the most spectacular sources of loss, and often are the leaks that will have the biggest impact on your customers because of the significant effort required for repair and the fact that you're often dealing with large quantities of water. But not everything surfaces. We do have small main leaks, and they can be particularly difficult to find and deal with. If you have a low density system, or if your sources are far away, or soil conditions prevent those leaks from surfacing. Hydrant leaks and valve leaks are also going to generally fall into this category, even though they're really appurtenances, they're not the mains themselves. And these can be really obvious, like is shown in the picture here, if the leaks are occurring near or above ground, but they aren't always going to, and it's a good idea to keep categorizing those different kinds of leaks so that you can find and identify and filter them and count them, so on and so forth. And then finally, the service line leaks. And these are often less obvious, but it's important to remember that any leak on your side of the meter is going to accrue to the utility as a loss, as a real loss. And the leaks after the meter could potentially accrue to your utility if you have a leak or repair rebate program in place. So if your utility credits the customers for leaks on the other side of the meter after a repair is made, completing the monetary credit transforms that water from revenue water to non-revenue water, and it pushes that volume into the real loss column. So just be aware of, if you have a program that helps your customers, it does impact your water audit and how you're tracking those things. And then, of course, there are tanks that leaks. I said that backwards. There are leaks at tanks and overflows at tanks. And the overflows, might be very obvious, assuming they're happening when someone's there and can see them. But there are times when they might not be. So this is a water tank in Alaska, and they can no longer fill it to its 19-foot capacity, because if they go over 16 feet, the system hydraulics cause an overflow at a tank that's about a mile away. It's completely out of sight when you're at this tank, but it's at a slightly lower elevation. So if they fill this tank up, the water's going to flow out the top of the other tank a mile away. And if they weren't aware of that, if they didn't understand their hydraulics, and if they were standing here looking at this tank, there would be nothing going on. They'd be filling it up and wondering why they could never keep it full. So just something to be aware of. And then this is one of 2 4 million gallon water tanks installed in 2012 at the Vandenberg Air Force Base to replace an old tank that had been leaking. And it had been leaking long enough that it had actually raised the water table at that location. So what we are getting at here is we want you to think about your infrastructure. Think about your tanks. Some tanks are built to channel leakage so that it can be recognized and quantified and addressed, and others aren't. So your ability to determine whether tanks are leaking, and if so, how much, is going to be dependent on your infrastructure and the level of effort and what kind of instrumentation you have. And if the leak is, visible, or if it's soaking into the ground very quickly, lots of things can impact your knowledge what's happening at the tanks. Now think about your tanks when you drain the tank to do any kind of maintenance or repairs. The losses that went through the leak are counted as real losses. So if you have a leaky tank and you go to fix it, you need to think about what went through the hole and was leaking, but the volume that you drained for the repair. So when you empty that tank, that goes to authorized unbilled usage. That's apparent loss. So just keeping track of those kinds of volumes is important. And you might have real loss in your production and treatment processes as well, if those are inside of your audit boundaries. So these losses aren't typically talked about too much because they're usually pretty small in comparison to the other categories. And I want to be clear here that this does not include water that's purposefully used or disposed of as part of the treatment process. Things like well flushing, that's not loss. Neither is brine disposal if you have like an RO treatment plant. Those are both purposeful actions. You're doing it for a reason. And those volumes would be considered authorized unbilled use. But you could have leaks and real loss between the wells and the distribution system. If the audit starts after treatment, these kinds of leaks wouldn't be included in the audit. But of course, you want to be aware of them. You want to be tracking them. You want to be analyzing them and probably repairing them at some point in time. So just another thing to kind of keep in mind. It's not one of the major categories, but definitely an opportunity for real loss. So with that quick review, let's run a poll to see which of the 4 categories I talked about you think typically contributes the biggest component of real water loss. So your mains, your service lines, your tanks, or production and treatment losses. So I'll give you just a few minutes. And remember, if you want CEUs, make sure you click in.
Looks like about 70% have responded. So we'll leave it up for a few more seconds. All right, I'll close the poll in 3, 2, 1. So it looks like 48% answered mains, 45% answered service lines, 3% answered tanks, and 4% production and treatment losses.
Great, thank you. I see a note that there was an echo early on. If it's still an issue for anybody, please let me know and I can try and address it. I hope that it hasn't been echoey this whole time. So I apologize for missing that right there at the beginning. So hopefully it's not an issue, but if it is, please let us know. And Tess, if you can kind of keep an eye on that, not Tess, gosh, sorry. Old habits die hard. Avery, if you can keep an eye on it, I would appreciate it. All right, so let's get to what the real answer is, or the correct answer is for the question. To some people's surprise, the correct answer is service line leaks. So to quote AWWA's M36 manual, in well-run systems, the greatest annual volume of real losses occurs from long-running, small to medium-sized leaks on customer service connections, except at very low densities of service connections. And oddly, these are the leaks that quite often aren't actually tracked closely in many water systems. They're often found and repaired, but poorly documented. This is something to think about when you're considering your data, the sources of loss, and what you want to track going forward. Getting back to my earlier point about long-running small leaks, here's a chart of loss volumes based on flow and runtime. And one thing this really brings home is the idea that the gushers quite often aren't the problem when it comes to real loss volume. And that's because they're big, so they tend to be noticed, located, and repaired quickly. the small, long-running leaks can lose more water than the big ones over time. There's a lot the audit doesn't tell you about real loss. In fact, it only tells you one thing, the magnitude. And if you don't have the rest of the audit dialed in, it's a little like looking at an iceberg. You've got an idea of how big it is, but you can't really tell for sure without looking under the water. The devil's really in the details. And here in particular, we're talking about the types of real loss that typically occur on the mains. So if we take a look, there are really 3 types of basic of leaks. So many leaks will surface and effectively announce themselves. Those are going to be your reported leaks. And then as a side note, the next question to answer for these types of leaks would be who reported it? The public or utility staff doing rounds. This is a good piece of information to keep track of as well. Second, we have leaks that don't surface, but are findable through proactive leak detection possibly. These are called unreported or hidden leaks. They're big enough to find if you're looking for them and might over time turn into reported leaks. But they aren't obvious and so may run for longer periods of time without being discovered. And finally, there's what we call weeps and seeps. These are the undetectable or background losses. They're named this way because they're happening in the background and often can't be found, even if you're actively looking for them using typical leak detection equipment. These are the small leaks, typically at the joints, that are basically unfindable. They're not reported, they're not detected using traditional acoustic equipment. And I did say traditional. There are new technologies coming out all the time, and it's possible that over time these categories are going to kind of blend together even more. If we're thinking about the satellite technology that's looking for chemical signatures of water or temperature differentials, these things might start to show up with those types of technologies. I do want to note that even though these leak types are separated into discrete categories, there's often a continuum from one to the next. So here, if we look at this graph, that's because, of course, some of the leaks get worse over time, as this image demonstrates. So this is a graph of a correlator recording showing the progression of a leak from mid-April through mid-August. And you can clearly see the acoustic signature shows that the leak increased in severity over time. But the other thing to note is that post-repair here, the acoustic signature is lower than it was when the correlator was, installed here in April. So what this shows is that we know the leak was running for at least 4 months, but the graph indicates that it was going on steadily for some time before that. This might be because the utility knew there was a leak and they were letting it run as an experiment, or it could be that this was a random search and the events around June tipped them off that there was a leak that they didn't get around to fixing until August. But this points to a major difficulty with quantifying real loss. And that is that even if you can find the leaks, it's really hard to figure out when a leak started. Further, if you're just starting to analyze your system, you may not know what the actual no leak baseline looks like. So it's possible that this correlator was randomly placed and no one realized there was an issue until that first spike in June. And only after that repair was it obvious that the pipe had been leaking when the correlator was first placed. So this is the reason for night flow analysis and other methods that we can use. So every leak has 3 time periods during its lifespan. The first is awareness, or how long it takes the utility to become aware that there's actually a leak. In the case of catastrophic breaks, that time might be short, but it might not. Next is location, the time it takes to locate a leak. And finally, there's repair, which is really the time it takes to isolate and terminate the leak once it's been located. For real loss purposes, you don't really care how long the repair takes. You want to know when the leak was isolated and turned off or stopped. How fast you're finding leaks and how fast you're fixing them can have a big impact on your real loss volumes. It's really all about the runtime. But of course, no matter what you do, you can't stop leaks from happening, and there's going to be a practical limit to real loss intervention. So no matter what, you're going to have some volume of real loss, and it's impossible to recover it all or reduce it all to zero. Some of that real loss you'll be able to recover or more appropriately reduce economically. In other words, you'll get the cost back for recovery or reduction. Some volume you could recover uneconomically. So in other words, you might spend $1 to recover 90 cents of real loss. And although that seems counterintuitive at times, there are reasons why that approach might be taken. For example, if you have a shortfall of supply, or if you're running up against a maximum state loss threshold, you might take some actions that cost you more than they return. And some volume just isn't going to be recoverable at all because nothing is ever perfect. Pipes are going to break. There are limits to what you can do, but that's okay because you aren't looking for zero loss, which typically is impossible, but instead you're looking for an economically acceptable level of real loss. There are 4 mechanisms you can use to reduce real loss or keep them economical. These are what I like to call potential areas for action. So these are the activities you can take to start controlling your real loss. And these are pipeline and asset management. So here we're talking about selection, installation, maintenance, renewal, and replacement of your pipes. Engaging in active leakage control. Looking at the speed of your repairs and the quality of your repairs, and pressure management. Using or not using each of these mechanisms will impact your overall real losses. But before you start applying these loss reduction techniques and taking action, you have to identify the nature, the quantity, and the cost of your real losses first. Real loss control isn't free, and in many cases, it's not even cheap. So you want to make sure that you understand the problem that you're having first, and then develop your control strategy. This becomes more important the less accurate your audit input data is. So for example, if you're using the audit defaults for theft and systematic data handling errors, and maybe your customer meter testing data is incomplete, or you don't have an accurate and complete picture of what's going on with apparent losses, that's going to reflect on the real loss volume that the audit calculates. And this gets back to our opening discussion. The real loss volume the audit calculates is based on all of those other inputs. It's not going to be perfect. What you have is an approximation. How reasonable that approximation is depends entirely on how accurate those other inputs are. So you don't want to go and take action based on bad data. We don't want you to have bad data and get an incorrect view of what's going on and then apply the wrong loss control tools. And like apparent losses, you need to tailor the strategy to your system's needs. Real loss control strategies are effective, but they can be labor intensive, they can be expensive, and after a point, they can have diminishing returns, particularly if they're misapplied. So this is one of the many reasons you want to track the results of your efforts, so you'll be able to determine which are effective and also understand where the sweet spot really is in terms of results for effort and expenditure. Remember, the audit is just the first step. It's not going to save water by itself. You have to take action based on the results of the audit and other analysis that you do. And with real loss, that additional analysis is really important. So we've put this guy going down the stairs for a reason, because audit creation and interpretation does get easier over time as you develop the processes to collect the information you need, to store it, to analyze it, and to report it. And the patterns start to become visible. So what other analysis might you want to do before taking actions to address real losses? Well, James is going to walk you through some of those options. So I am going to turn things over to James at this point.
All righty. Okay, so component analysis is kind of a key part of developing and evaluating your loss control strategy next steps. And this is something that we've touched on a bit in prior sessions. And so I'm going to dig into this a little bit deeper, and then we'll move on to some examples of those 4 pillars of real water loss control that Don mentioned and kind of show them in action. And I'm starting with component analysis because this is kind of the second step after doing the audit. It's a really useful tool for corroborating or refuting your audit results, and also for digging deeper into loss volumes, particularly real loss, but also the other volumes that maybe you're estimating in the audit itself. It's really helpful also to help you measure the effectiveness of your various water loss control strategies that you might be implementing at a granular level, and also help you decide which ones to implement. As we've said before, the audit is a top-down process where we're looking at the volume of water that we're putting into the system, taking out all of the consumption that we can measure and estimate, and coming up with some loss values. So, we're gathering that source data and making our estimates. And our end result is this volume of non-revenue water, which includes our 2 loss categories and the costs and values associated with them, a bunch of KPIs as well. But as we've said, the audit itself isn't perfectly accurate if you're doing a lot of estimating. So ideally, you want to be able to corroborate both audit inputs and outputs and results so that once you've got a total loss volume, you can start to pinpoint the sources and the causes of loss before you sort of jump into solving the problem. You really want to know what it is. For confirming or refuting those audit outcomes, particularly real loss, component analysis is the way to do it. And some of you are probably familiar with the concept, but for those of you who aren't, it's essentially trying to calculate losses from the other direction. So the audit kind of starts big and gets small. In component analysis, we're basically starting from the bottom and working our way up, trying to ascertain the volumes of water in specific categories by looking at individual components and data that we have about them. And then we use that information to try and verify the volumes that the audit's giving us. So we're essentially creating the audit or parts of it in reverse. So it's basically exactly what it says, looking at the components that make up the individual values in the audit. And if we can do this, it kind of will help us improve our understanding of what's going on, and also potentially help us calibrate our audit and our audit results. Can help us sort of reevaluate some of the estimation that we've done, for example. Because the water audit itself, it's really just a model of system inputs and outputs. And as we said, there's a certain amount of uncertainty associated with them, particularly the real loss components, because it's just what's left over. And so doing a component analysis, if you have the data, really helps you dial that audit in, both the individual pieces and then, again, confirming and refuting your loss audit results. And trying to do a component analysis, even if you don't have the data, really gets to highlight the gaps that you might have in your data collection and data analysis processes. Maybe gaps that you didn't see when you were first developing the audit, because the audit is much more of a summary look. There's really 2 ways to think about component analysis. So component analysis in general is trying to discern the whole by looking at its parts, which is how you can apply it to the other categories in the audit itself. I think a puzzle is a really good metaphor. The picture on the box tells you what it's supposed to look like, and then you have to get all the pieces and sort them and figure out how they go together and see whether that picture that you come up with is actually what the box showed you. And if you're like me and bought a lot of puzzles from Goodwill back in the day, sometimes what's on the box is not what you end up with. You can take a total out of the billing software and then also try to assemble that total looking at, summarizing individual customer classes, for example. You might remember my example from our last session about the system with the faulty archived account query. They did a query that pulled out the total volume and it was wrong. We fixed that by doing a component analysis. We essentially went into the database, looked at the individual pieces, added them up, and realized, our summary is not correct, and here's where the problem is. So that's kind of the general concept. When applied specifically to real loss, we're talking about leakage component analysis. And that's recreating the loss volume from event data that we've collected, hopefully, about them. So typically, we've got those 3 categories that Don talked about. A leakage component analysis focuses on those 3 categories of event data. So mains information, service line break information, and storage facility information. And we try to recreate that lump sum from its constituent parts. And as Don mentioned, it's often quite difficult because you don't know when things started, but doing this will give you a better picture. as Don noted, and as we looked at in our poll question earlier, quite often half or more of the real loss comes from service lines. Doing component analysis is the kind of thing that can help you pinpoint that sort of thing. So if you have data on all three of those categories, or maybe only one or two, you can still start that process and make your real loss picture clear. Because in attempting to do it, it sort of shows you what you know and also what you don't know and aren't tracking. One of the nice things about leakage component analysis is there are guidelines as to what information you should track and what level of detail you should keep on it. So doing a leakage component analysis, in particularly with real loss, serves a couple of related functions. It's corroborating or contradicting your real loss volumes that the audit produces. That in turn gives us insight into the accuracy of the audit, can help us calibrate it by maybe changing some of those assumptions, as we've said. And it also helps you determine where your real losses are occurring, sort of in general terms, which the audit also doesn't do. It just gives you that lump sum. Because you're doing an analysis of each of those loss areas. And finally, it kind of helps you see what's going on in the background. As Don indicated, there's three kinds of loss on mains, for example. There's the reported, the unreported, and the background. Now, the unreported stuff you can find if you're looking for it, but you might not be. So if you can sort of quantify the reported leaks, that gives you a volume that's falling into these other two categories. So basically, it allows you to sort of get more and more granular in your understanding of what's going on in your system. It's all about quantifying the knowable, or maybe more accurately estimatable, and seeing what's left so that you can think about, do I actually need to go do leak detection? Is there a lot of loss on my mains that I can't account for by looking at event data? As I said, in the context of real loss, we talk about the leakage component analysis. There's actually a tool for this. It was developed by the Water Resource Foundation. It's called Project 4372, and there is a suite of tools. They're Excel based, and essentially you can take your event data, you can put them in there, and it will sort of model your losses for you and give you an idea of what's going on in the background, what's likely reported, what's likely unreported. And again, trying to do that process is really useful because it just shows you really clearly what you aren't tracking. If you have that break and repair time data, you can really start digging into those results and splitting it up into its constituent parts. It is a fairly complex and data-heavy tool in that you have to have information to put in it, but you can also do some estimating, and it has the ability to do some modeling for how changing repair times might impact your losses overall, because there's a direct correlation, obviously, between how long something runs. And there's also some information in there that you can use to sort of estimate volumes that are coming based on pipe size and leak size and things like that. But fundamentally, the biggest, I think, eye-opener for people that try to do this the first time is that it really shows you what you're not tracking and could be. If you don't maybe have quite that granular a data, maybe all you have is a map of your system that shows you what materials you have and a list of breaks that you can identify by material, all is not lost. You can do a more simplified analysis called a break rate index analysis. This is a tool that we developed to let systems do sort of a broad stroke overview of how your system's particular break rates by material stack up to national averages. And basically, if you can identify main breaks by material, and know how much of each material you have in your system, you can put that information in and relatively quickly generate yourself a dashboard like this. And basically, the way the break rate index works, it's very similar to the infrastructure leakage index in the audit, in that it's a non-dimensional index where 1 means that your pipes of that material are breaking at the US-Canadian average. A 2 score means that they're breaking at twice the average, and a 0.5 means they're breaking at half the average. In the bottom right corner is the total here. And what this is essentially a weighted average for a theoretical system with your particular pipe makeup. So, however many miles of each material of pipe you have. And if those were all breaking at the average rate, and then dividing that by your particular systems. So what I want to point out with this is that if you look at the total, you see we've got a BRI score of about 0.7. So significantly below 1, which means overall in my system, pipes are breaking at a lower than average rate. But to get back to that iceberg metaphor, the devil's in the details. In this particular utility, we've got an issue with steel in particular that's breaking at almost 18 times the national average. And then we might also want to be keeping an eye on concrete because that's a little bit high, and these other pipe, non-classified pipe. So what this really kind of does is show you that you might have a big problem on a small quantity of pipe. Addressing that steel pipe might have a significant impact on your real losses and repair times and repair costs and various other things. But to use this tool, you have to have some basic information about the material makeup of your pipe and what kind of pipe each break was on. If you've got that, this is something you can do in literally about 20 minutes. If you don't, collecting a year's worth of data to develop this kind of analysis is not hard, and we can help you with some suggestions about data collection tools and things like that to do. So this move brings us to our next poll question, which Avery's going to bring up here, which is about what kind of break data you track and how you use it. So we had to kind of jam the answers in here. There's, and this is a select all that apply. So do you collect main break data? Do you collect service line data? Don't you use that for break analysis, or do you use it for example, driving loss control or other? And then last but not least, not a system.
All right, about 60% have voted, so we're going to leave it up for about 15 more seconds. Remember to get your answers in. Okay, the poll is closing in 3, 2, 1. So it looks like 49% answered main break data, 39% service line break data, 26% we don't use our break data for analysis, 19% we analyze our break data, and 25% not a system.
Okay, that's about typical. That's what we usually see. For those of you who are tracking main and service line break data and using it for analysis, kudos to you. I think it's really important, not just for water loss control. Honestly, I think that for capital improvement, it's actually much more important because using break data, as I will show you in an example here in a moment, is really useful for figuring out how you're going to repair and replace pipe. For those of you who don't use it for analysis, you might be a really small system and not need to, but I would potentially second guess that question. A lot of systems kind of don't collect it and use it because they don't have a lot of leaks right now, and that's sort of the justification. I think over time, every system develops more and more leaks, and if you've been collecting information strategically, over time, you start to see those patterns develop as opposed to suddenly realizing you have a problem and then not having the information you need to actually address it. So, for those of you who aren't collecting it, think about maybe starting it. It's actually a relatively inexpensive and effective way of doing things. Our next session is actually going to be about data collection and mapping. So please tune in and maybe I can convince you to join the data collection side of things. All right, so we've talked a little bit about component analysis and those sorts of things. I want to move on to actually doing something about it, reducing real loss and what kind of tools that you can apply. And we sort of call all of the possible things you can do the loss toolbox, and in this case we're talking about the real loss toolbox. So as Don mentioned, there's sort of 4 different categories or 4 pillars of loss control activities: asset management, active leakage control, repair speed, and pressure management. But obviously within these categories there are a lot of different things you can do, and this is not a comprehensive list. But under asset management, collecting and analyzing break data, hint, hint, is one of the things you can do. But main replacement and repair techniques, and service line replacement and tank management fall sort of into this category. Under the active leakage control, there's different kinds of proactive leakage control that you can do: acoustic surveys, satellite surveys, also night flow analysis, sort of figuring out what that baseline leakage level probably is. Speed and quality of repairs is fairly self-explanatory, you know, whether you could or should improve either the speed or the quality or both of the repairs that you're doing. And then pressure management kind of falls into two broad categories. There's dealing with overall peak pressure and overall system pressure, and then also locating and eliminating pressure transients. So those surges from water hammer, like when pumps slam on and off, or when valves are open and closed rapidly, being able to track those in your system and reduce them. These and other activities, as we said, sort of fall into this thing we call the real loss toolbox. There's a copy of this along with other tools that you can use for other kinds of loss attached to our applied activity today. But basically on the left-hand side, we've got the kind of loss it applies to. In the middle, we've got the type of activity. And on the right-hand side, we've got a broad estimate of cost. So, you know, collecting and analyzing break data is a relatively cheap thing to do. Doing a night flow analysis is a little bit more expensive. And of course, you know, replacing mains is a very high cost option. So there's a lot of different tools here. And I'm going to walk through an example for each of our 4 pillars and kind of show you how these have been applied in real life. And I'm going to start with asset management. I'm going to do these in a slightly different order, just because I think it makes a little bit more sense here. So collecting and analyzing break data and then dealing with using that to sort of drive main replacement is really important. This is the asset management tool. Probably heard of asset management. It's essentially an overall approach to managing utilities, or any other business for that matter, really, where you're trying to make data-informed decisions to figure out what to do, how to do it, and how to get the most cost-effective, efficient results for your utility. And we really think of water loss control as kind of a subset of asset management, and water loss control activities can really become part of your asset management plan. And many things in your asset management plan will have co-benefits as they relate to water loss control, as we will see with this perfect example here. Used to be thought of as that asset management was kind of a big utility thing. We and a lot of other providers have shown again and again that small systems are really well equipped to do this kind of thing themselves as well. This example that I'm going to show you also shows you that you don't necessarily just have to use the water audit as a starting point for activities that will have positive impacts on water loss control. Although doing the audit is really recommended because that helps you sort of keep track of the efficacy of what you're doing. So the background for our example here is we've got a system. It's our home system, actually. Albuquerque had been spending about $5 million a year for pipe replacement, and they were having no impact on their annual break rates or water loss volumes. And they were trying to figure out what to do about it. And their solution, which we helped them with, was to crunch available data and develop an asset management plan. So basically looking at their pipe replacement practices and the results, and to see whether they were going about that process in the correct way. So this is a map of about 8 to 10 years worth of breaks, and they're color-coded by pipe material. And the first thing you probably noticed looking at this is that most of the dots are red and yellow. And so what we did is we looked at this and we sort of filtered out the also-rans and just focused on those 2 big categories, which accounted for the vast majority of the breaks. And when you look at this example here, this image here, you see there's about a 50-50 split between. So these are cast iron pipes and steel pipes. And it might not seem like much of a concern until we compare this to the pipe material distribution, which is very, very different. The blue pipe here is cast iron, the red pipe is steel. And overall in the system, steel only accounts for about 5% of the system, but half of the breaks in this system were occurring on that 5% of the pipe. And now we start to see the issue. You know, steel pipe breaking at 10 times the rate that the cast iron pipe was, even though the cast iron pipe was significantly older. And this is actually the kind of issue that the BRI tool that I showed you, the break rate index, was designed to highlight without having to do an in-depth mapping process. This utility was actually the inspiration for that tool. So knowing that they've got a big problem on a small part of the system, the utility was able to change how they manage pipe replacement by focusing on the steel pipe, and not just steel pipe, but actually sort of using that break data to figure out what steel pipe was bad and what steel pipe was worse, because even among the sections of steel pipe, there were still some sections that were in serviceable condition. So they took this information, rethought how they were doing things, developed an asset management plan that changed the strategy for pipe replacement. Basically, they started doing targeted pipe replacement based on some real data rather than just looking at the oldest pipe in the system and going with that. They implemented this asset management system in around 2011, and within 5 years, they'd reduced their break rate and associated costs by 45%, which is pretty dramatic. They also had a 5-year cost avoidance of about $9 million, and that's $9 million that they were able to spend doing other things, valve replacement programs, other kinds of activities. And the interesting thing about this process is they did not change the amount of money that they were spending on pipe replacement. They're still spending $5 million a year. They actually replaced less pipe in the system because they were doing these targeted approaches. So they had more initial sort of setup and breakdown costs as they were moving around the system, but it was a much more effective way of dealing with the pipe breaks, as the results here clearly show. And I don't have the loss control numbers, but there was a concurrent drop in overall real losses as well that sort of tracked this. So good example, I think. Moving on to speed and quality of repairs seems pretty obvious. It's pretty straightforward if you track this information, but a surprising number of systems that we work with cannot tell us how much they spend on an average service line or main break, or how long those repairs take, because they just don't track the information because they don't see it as being valuable. And I'm not talking here about just speeding up your repairs for the sake of speeding it up. You want to do it if it makes sense, when it's evaluated, given the triple bottom line and the costs associated with the water that you're losing. So this is kind of a thought exercise. Just think about like what the average leak in your system looks like. Are they, typically those gushers where you become aware of them quickly, but maybe it takes you longer to repair? Is it maybe something a little more like this, where awareness takes more time? There's a lot of different ways this can play out, and obviously different leaks are going to play out differently. But knowing what the average in your system is really useful, because then you can sort of start to look at what would be the impact of speeding up the repair. If I can cut my repair time in half, what does that save me in terms of losses, et cetera? And you really have to do a cost benefit analysis to see whether there is a case for more rapid response. Some costs that you might have is having additional staff maybe on call to be able to deal with stuff at night, maybe additional equipment or resources or spare parts that you don't normally track. And then you have to weigh that against the benefits of actually speeding things up. Reduced water loss would be a benefit, and obviously not having to produce the water that you're just pumping out of the hole in the pipe. Maybe reduction in damages from catastrophic failures. Letting things run longer so there's more damage. But then there's also social benefits, customer goodwill, and there may be other economic benefits. So this is really about a cost benefit analysis. And the neat thing about data collection is you can leverage break data along a lot of different lines if you collect the right pieces of info. So this map you're looking at here is from a system we worked with in Texas, and we started out looking at this as an asset management program, but one of the things that they tracked was repair speed. So in addition to tracking the location of breaks and the materials that breaks were on, we added a time element to this. And you notice there's 3 different colors of dots: green, yellow, and red. Green was repaired within 24 hours, yellow within 48, and red's anything that took longer than that. So 80% of the leaks were repaired within 48 hours, 70% of those within 24 hours. Some of the other breaks, about 18%, took longer than 48 hours. And then we started noticing, there's some correlations in a few places between long repairs in areas that are having repeated breaks. But because we had this information and we were knowing how many people were involved, what the labor costs were, we could start to do that analysis to see whether sticking to the current repair scheme was cost effective, or whether it might be more cost effective to speed it up or slow down. So when you're thinking about this aspect of loss control, you really want to think, do you know how fast you're fixing breaks? Can it be improved? If so, how can it be improved? And then finally, the real question is, should it be improved? Because in some cases it's going to make sense, and in others it's not. But that's only half the picture. That's the speed. Quality is the other side. This is a leak actually in our director Heather's neighborhood. There have been 5 leaks in the same location over the past 6 to 9 months, and the utility just keeps digging up the street, making a repair and repaving it. And if you look at this picture, you might notice that there's a spot right on top of a recently repaired section of pipe because it's leaking again. And this has been going on for a long time. We can tell because on the upstream side of these leaks, uphill side of these, it's dry as you would expect out here in the desert, whereas the downhill side is all lush. So this gets into sort of the repair approach. You know, is this utility doing the right thing by continually coming back to the same place? You know, if this was an occasional issue, that would be one thing, but this is actually more the norm in this particular town. It took them 7 days to repair this, so maybe there's a speed issue as well. But here the fundamental question is, was repair actually the right solution? You know, this area is known to have substandard pipe. It's old polybutyl stuff that was installed when these developments were made, and this kind of break pattern happens all over the town. It might make more sense in their cases to replace pipe as soon as they notice a break, because the typical pattern is you have one break, you repair it, and then you're going to have to come back time and time again. So if you're tracking this kind of information and are aware of it, you can start to do cost benefit analysis. It might cost a little bit more up front to, you know, yank a service line out and replace it with something that's actually going to last on that first service call, but by doing that, you avoid all those return calls. Again, if you've got the information, you can do the cost benefit analysis and see whether that makes sense. So speed is one piece, quality is another. Moving on to pressure management. This, like asset management, is one of those tools that you can use kind of in the absence of any other information, because we know there's a direct relationship between pressure and leakage. If you've got holes in your system, the lower the pressure, the lower the losses will be. You know, the same leak at low pressure might dribble, whereas as you start to jack the pressure up, it starts to gush. And this is a pretty linear relationship, and we can use that knowledge to kind of impact losses in our system by thinking about optimizing system pressure. Version 5 of the audit actually has a KPI where they look at losses per pound of pressure, because in the typical pressures that utilities work in, there's a more or less linear relationship between loss and pressure. This graph happens to be from a system that we worked with that was looking at system optimization, and you can see here that by dropping the overall system pressure from about 65 to 55 PSI would result in about a 4 gallon per connection per day loss reduction, which is fairly significant. So, you know, you can use this kind of information to see what the likely impact is going to be. It's obviously not going to be perfect, but it's good enough for planning purposes. So, you know, there's a water loss benefit to reducing pressure, assuming that, you know, reducing pressure is a viable option for your system. You know, if you're running at 35 PSI, you probably don't have anywhere to go. But if you're a high pressure system, there might be areas within your system that you could reduce the overall system pressure by using a PRV to you know, reduce the pressure and then reduce the associated loss. But there's another aspect of pressure reduction that is really helpful, and that has to do with, you know, finding those transients and getting rid of them. Because, you know, when a pipe gets put in, it might have a very, very high failure pressure, you know, 150, 200 PSI, but for every pipe, over time, you know, pressure surges are going to happen. When it's new, the pipe can handle it, it's not a problem. Over time, that failure pressure threshold is going to be impacted by things like corrosion of its metallic pipe, or traffic loading, or ground movement, temperature swings. All of these are going to impact, you know, your pipe over its life and sort of reduce its ability to handle pressure surges. And if you keep having them, and, you know, over time your pressure threshold is dropping, eventually you're going to start to have breaks. You know, after, you know, a couple of decades in the ground, that 150 PSI might be dropped down to 100 or less. So think about not only overall system pressure, but pressure in specific areas, and the ability of your pipe to handle pressure surges. And this is a piece of break data that often isn't captured, you know, what the pressure is at a particular location where the break happens. Because if you're collecting that information, and you should be able to find it out if you have a hydraulic model, you can start to track and see whether there's a correlation between pressure and breaks. And if it's possible to keep sort of the overall system pressure below that or eliminate those transients, you might be able to reduce the number of breaks that you have in your system. So when you're thinking about pressure in your system, think about optimizing it overall, trying to determine pressure at failures, seeing whether it's possible to maintain your system pressure below that threshold. Obviously trying to reduce those pressure surges if you can, because if you don't deal with pressure over time, just like everything else, break rates are going to go up. And the neat thing about pressure optimization is there's a whole lot of co-benefits that go with it. If you can do this, obviously there's going to be a direct impact on your non-revenue water. It will go down. But if reducing pressure reduces breaks, then you've got lower repair costs. If you're reducing pressure, you're going to lower your energy costs because you're not pumping at as high a pressure. And possibly the biggest benefit of this is that deferred asset replacement possibility. If you're babying your pipes, kind of keeping track of what's making them break and dropping that your pressure volumes or values down below that, you have the potential to help defer asset replacement, and that's money you don't have to lay out. So think about your pressure in your system, think about whether you're optimizing it, think about if you can, because even a small reduction should help. But obviously recognize that in some cases you might not be able to just because of your particular system. Last but not least, we're going to look at active leakage control, which is, fine. Yep.
Just a time check. I think maybe we should just go ahead and move to the wrap up.
Okay. So when you're thinking about leaks, just think about a couple of things. It's not so much whether you should do it or could do it, but pace your leak detection to what you can actually fix. Try to match the technology to your system specifics. Make sure that your leak detection practices and goals are aligned, and then obviously match your budget to what you can do. Think about whether you're tracking your leak detection efforts, thinking about optimizing them as well, and think about whether you can change your strategy to make it more efficient, because leaking detection your entire system every couple of years might be an effective way to do it, but kind of like with our break analysis, doing pinpointed leak detection is often a much more cost-effective approach. Those tools and information about those and a lot of others are available on our website. We've got a whole water loss control switchboard that you can look at. That's available at our website at SWEFC. And one of the things on there is a template guidance document designed for sort of documenting your auditing process. And we're going to give you an applied activity that you can download from the check here. That is essentially a bit of a thought piece. It's kind of a team exercise on reviewing the real loss volumes and values that your audit gives you, making those initial assessments about whether loss control action is appropriate, and if so, what action you can take and maybe should take. So with that, I will open the floor to questions if we have any, and put up our contact information for anybody that wants to talk about any of these issues in much more depth.
So the presentation that is posted, for those of you that are interested in the slides that James cut out, they are in that presentation, and it was just a couple of slides. So we didn't cut out too much for time's sake, but they are there, so you can take a quick look at them if you want to in the downloaded presentation. And we do have a couple of questions about the slides that we skipped, and one other question. So the first question I think is I've answered directly, just in case we ran out of time, and we are out of time. So if you have to go, we understand. I tried to answer your questions directly. If you're able to stick around, we'll answer these couple of last questions. But thank you so much for your time and attendance, and we'll answer these last couple of questions if you're able to stay. So James, the question that came in is, how is health risk or aesthetic quality of water factored into repair speed considerations? And so I think what we never want to compromise health or safety when we're doing a repair. But the point at which we shut the water off to make the repair is no longer, that repair time becomes ended there. So what we're really talking about is not the time it takes you to fix the leak, but the time it takes you to identify the leak and then get a crew out there and then turn the water off. So if it takes you 2 days, or if it takes you 2 weeks, or if it takes you 2 months between when the leak's identified and when the leak is repaired, that's the time we're talking about. So hopefully that helps clarify that. We never want you to say, oh, we've got to fix this really fast and maybe we won't chlorinate this time, or maybe we won't flush, or we never want to compromise health and safety ever. So hopefully that helps answer that question and clarify what we mean by repair speed. We're not actually talking about how fast you can put a clamp on the pipe. We're talking about how long does it take you to get out there to actually make the repair. So it's a great, and maybe we should clarify our terminology a bit, James.
Yeah, well, yeah, because repair speed, there are different aspects to it. You know, there's the health and safety aspect, there's the water loss aspect, but, you know, we mentioned the triple bottom line. There's also, you know, the social aspect of any activity that you do. You know, if you're just not repairing things quickly because you don't feel like it, or, you know, if you can speed things up, that may have a positive benefit, and obviously speed things up safely, positive benefit on the way your customers view you. We have a question about the entire system every 4 years.
Yeah.
So I'll go back to that slide and just kind of walk through that section real quickly. And the point is that, you know, not every leak is going to surface, you know, and not every leak can necessarily be found. You know, like this example right here, been going on for a very long time. It's bone dry above it. You know, this is a leak that's not going to surface. You know, there's a lot of different options for doing surveys, and my point here today was not really to sort of go over the types of leak detection you can do, but having you think about strategizing how you do your leak detection. So, you know, we worked with a system that sort of, as a standard operating procedure, did leak detection on a quarter of their distribution pipe every year, and they basically worked around the system like clockwork. They did, you know, the same section every 4 years, doing that is not necessarily bad. The issue was that they weren't necessarily analyzing the data that they were getting from it. So, you know, the pros of doing that is they had a really good understanding of their system and how it was changing over time, and they would put that information to GIS so they could sort of track where the breaks were going. Problem is they sort of didn't do the next step, and they also had some financial issues. So they were finding leaks, but not necessarily repairing them. And they would leak detect a section, find some leaks, go back, repair them, but then they wouldn't do a secondary sweep. So one of the things we know is that small leaks are really loud. They can often mask larger leaks that are happening, you know, somewhere in the area. So they were finding a lot of small leaks, but they weren't necessarily going back and sort of checking their homework after they were done to see whether they'd caught all of the leaks. And the other thing that they were doing is inspecting a lot of good pipe that didn't have many leaks at all and had been sort of shown by repeated passes to not have issues. So they were essentially spending money checking stuff that they probably knew was okay in the first place. So it's really a matter of you know, looking, if you're going to look for leaks, do it strategically. And you might start with a sweep of the whole system and then compare that information to what you know about leaks that are surfacing and that are reporting. Because if you look at it sort of all in a bucket, it's kind of like that iceberg thing. You know, you don't understand the details, but what you might find is that in your particular system, most leaks surface, and that leak detection isn't maybe a cost-effective way of dealing with things. You might conversely find that most leaks don't surface, and that leak detection is. I'm working with a system down in Florida right now that has this break data and really hadn't bothered to map it. And so one of the things that I had them do was pull what they had and just stick pins in a map on the board and see what that shows you. And the response to them doing that was, you know, James, that was eye-opening, because what they found, and this is typical, leaks are never evenly distributed through a system. They found that most of their leaks were concentrated in a couple of areas. They happened to be one older section of town and one that I think had a lot of tidal influx, where tidal activity was moving pipes around. In their particular situation, leak detection doesn't work very well because of the high water table, but tracking that information and plotting it on a map really would allow them to say, well, maybe I don't have enough money to do leak detect the whole system, or maybe the kind of leak detection I need to do for my system is very expensive, but I don't need to do it everywhere. Let me focus on this area that I know is a problem, and then see what happens. Find those leaks, fix them, see what happens. So again, it's not necessarily about not leak detecting. It's making an economic argument for leak detection, because like with everything else, there's going to be diminishing returns. At some point, the money you're spending on it is not going to be returning water value to you. And again, this is another way of thinking about that whole how are we going to value our leaks? Are we going to do customer retail unit cost? Or are we going to do variable production cost? Because if you're looking at it variable production cost, it's not worth much. If you're looking at it customer retail unit cost, however, that's a whole different situation. And that's a legitimate way to think about it. I think it was the state of Oklahoma looks at all real loss at customer retail unit cost, because Desert Southwest, they want people to pay attention to this. And in some cases, they're particularly, like for example, if you're a groundwater system, water that you don't lose is still in the ground for you to take out later. So that kind of argument makes sense. But the whole point here is to basically, if you're going to do something, do it right. Track the information, and to the extent that you can, use that information to really direct your efforts as you go forward. Nothing in your system is static. Leaks patterns are going to develop. Leaks are going to move around the system as you fix and repair things. So you want to be keeping on top of that and make sure that you're optimizing your leak strategy, optimizing your leak detection efforts, and then periodically reviewing whether the strategy that you currently have in place actually still makes sense.
All right, I think we can turn things back over to Avery.
All righty.
Great, thank you both so much. I would like to extend a huge thanks to Don and James for presenting with us today. Following this webinar, you will all receive a follow-up email with our survey, a link to the recording, and you will also receive today's handout and a copy of the slides. As a reminder, session 6 of this series, Mapping the Water Loss Control and Asset Management Nexus, will be held in 2 weeks from today, on Thursday 28th from 1 to 2 p.m. Eastern Time. And thank you all again, and big thanks to Don and James. So I hope to see you all in the next couple of weeks.
Thanks again.